Okay, we've seen when we have this configuration. So we've got a graph and we've got the equation of the graph, we've got the x-axis, and we've got an area between the graph and the x-axis between two vertical lines at A and B. So we know that this is an integral. Okay, so we could do that. But you may not be able to integrate f of x. In fact, it may not just be that you can't do it. We haven't learned that much integration yet. But even after you've learned all the integration there is to be learned, there are still some standard functions that do not integrate to standard functions. So in a sense, there are integrals that are forever just not doable algebraically. So we use a numerical method, and you may have done this at GCSE where you actually had to draw the graph and do something like counting squares, or maybe you've done the kind of calculation we're going on to. What we're going to do is we're going to approximate this area. What the idea is to this is the main area. We're going to subdivide it. I'm going to subdivide it into 3. Okay, the more subdivisions you make, the more accurate this method becomes. Okay, but I only want a few because I want to show you that this is an approximate method. So the method we're going to use takes each of those, we call these strips. So we say n equals 3 here, and n equals 3 because there are 3 subdivisions, 3 strips. Okay, now each strip is really, it's got 2 straight sides and 3 straight sides, the bottom and these 2, and then the top is not actually a straight line, but I'm going to treat it as if it is. So we're going to approximate each strip by a trapezium. It has 2 parallel straight sides. It's got a straight side along the bottom, and I'm approximating the curve with a straight line across the top. So we're going to, in this case, with 3 strips, we're going to have 3 trapezia. That point there should be exactly on the curve. So let's actually give some things names, some dimensions names. So we've got 2 x values, a and b. Okay, we want to name all 4 of these x values. So when there are 3 strips, there are actually 4 x values. These x values are called x0, x1, x2, and x3. Okay, and the associated y coordinate. So this is the point x 0, y 0. So I have to start counting from 0, or I choose to start counting from 0, so that the last one, we said n was 3, and we end with x3, having had 4 x values. To do that, I have to start counting from 0. So this is the point x1, y1, this point x2, y2, this is the point x3, y3, which means the y values, okay, the y values, y0 is the length of that vertical, y1 is this vertical, y2 is this vertical distance, y3 is this vertical distance, okay? And to work out the trapezium, you need to know the parallel sides, which we've now given names to, and the distance between the parallel sides, I'm going to call h. I'm going to assume these 3 strips are all of equal width, h. And of course, h is going to be 1/3 of the total gap from A to B. So in fact, there's this recipe for h. If I want to know what h is, I do b minus a, because that's the total distance from A up to B, and then I divide by n, where n is the number of strips. Okay, and then I've got to think of how would I work out the area of these trapeziums and add them together. That's going to give an approximate value for this integral without doing any integration, because these y values are calculated without integration. Whatever the formula for f of x is, I feed these x values into that formula, and out come the y values, and I didn't need to integrate anything. Okay, so let's think about the first trapezium. So the area of a trapezium is half the total of the parallel sides multiplied by the distance between the parallel sides. Well, these parallel sides are called y0 and y1. And the distance between them is the thing I'm calling h. And then the next trapezium is going to be a half of y1 plus y2 times h. And the next trapezium is going to be a half of y2 plus y3 times h, and it's going to be plus dot dot dot, and then the last trapezium is going to have, well, the last one is going to be plus yn, the second value. So the value before that is yn minus 1. So in the case n is 3, this would be y2 plus y3. Oh, in fact, it would be that one. For the n equals, the case I've drawn, it's just these 3. But if there are a lot more strips, I'd go all the way up to the last one, which is this one, times h. But this is an inefficient way to do the calculation, because every single one of these terms has got a half and an h. So I can take out a common factor of a half h, And then if I think about the remaining bits, I've got y0 plus y1 plus another y1 plus a y2 plus another y2 plus a y3. So I'm going to get 2 of everything apart from y0. y0 is on its own. And the very last one, yn, there's not any more yns, but there'd have been another yn plus 1. The second term in the previous one would be a yn. So y0 and yn are kind of special. They only get counted once. But then all the other trapezia, all the other y values, okay, have to be doubled. So we do y1 plus ... plus yn minus 1. And if we want to, we can put brackets around that. I don't know why you would, but that is what the formula book has chosen to do. What we've just arrived at is in the formula book. Here it is. So the integral, they've called that, I wrote f of x, written y. Okay, and then this is exactly the formula I've just written down, and this is exactly the recipe for h that I wrote down. So we're just going to be applying that formula from now on. So in this example, we've got a curve y equals sec of x. Okay, and we've got the area between the vertical lines at 0 and pi by 3. So the actual integral that I'd like to do is pi by 3, lower limit is 0, to pi by 3 of the function sec x dx. And of course you could type this into your calculator, I suppose. Your calculator can do this approximation. So why do we use this complicated formula and work out individual values on our calculators, using a long calculation on your calculator when your calculator's got a button that can go and do it in one go? Well, actually what the calculator does is a slightly more sophisticated approach to what we're doing here. So there is a case for knowing how the calculator has been programmed in the first place to do this kind of approximation. Okay, or you could think this is just something that is left on the syllabus because people don't like change and they like teaching what they've taught before. Anyhow, not my choice, but it's on the syllabus, so we're going to learn how to do it. And this is the old style of exam question where they didn't want to give too many marks for filling in the table, so they set it up for you. Okay, but let's think about where these values come from. Okay, so they're choosing to use, we've got 1, 2, 3, 4, 5 x values. That means they're choosing to use 4 strips. Okay, remember the x values, if you like, if you give them their names, are from x0 up to x, so that'd be x0, x1, x2, x3, x4, so we've got 4 strips. It's a good idea, I think, to draw them on the diagram. So there are my 4 strips, and here are my 1, 2, 3, 4, 4 strips, 5 x values. And if there are 4 strips, and this is pi by 3, then basically the width of each strip, h, is going to be, well, the gap from 0 to pi by 3 is pi by 3, and I divide that by 4, so it's pi by 3, divided by 4, which is pi by 12. And if you like, you can use this recipe here. So b is pi by 3, a is 0, and n is 4. Not 5 x values, but 4 strips. But I think drawing the strips on the diagram, okay, makes it really convincing they're pi by 12 wide. So that's why the first x value obviously is 0, and the next one is pi by 12 more than that. And then add another pi by 12, you get this. Add another pi by 12, you get that. Another pi by 12, you get that. If you like, I mean, if you're doing it on your calculator, of course, you don't need to do pi. If you've got fractions of pi and you want to add them up, you can do a 12th plus a 12th, and you get a 6th. And then you do a 6th plus a 12th, and your calculator tells you it's a quarter, and so on. All right. Now, to get the y values, where did these come from? Well, they came from the formula y equals sec x. So therefore, they've done sec of pi by 12. Here we've got to do sec of pi by 6. Here we've got to do sec of pi by 4. Now, of course, sec of pi by 6 is 1 over sine of pi by 6. It's 1 over cos of pi by 6. This is one of those ones that's exact, actually. Cos of pi by 6, your calculator will tell you, is root 3 over 2. So this is 2 over root 3. If you do it on your calculator, it will simplify the surd, and it will probably tell you, what will it tell you? It will tell you that it is 2 over root 3 is 2 root 3 over 3. And for this one, sec of pi by 4, well, cos of pi by 4 is 1 over root 2, so this is just root 2. Okay, and if you can fill in exact values, that's a good idea. Here they've had to round it to 4 decimal places. Now, if you're going to round that to 4 decimal places, I'm not going to trust or 4 significant figures. I'm not going to trust my final answer to more than 3 significant figures. They've done that for us. Okay, but if you can leave it as an exact form, then I recommend you do that. So complete the table above. It doesn't say put them into 4 significant figures. I've written them below because my writing's too big to fit into those boxes nicely. So now we've got to use the trapezium rule. So what I've got here is all my y values. So I'm just going to do this calculation here. I've already got my h is pi by 12. So I'm going to do half times h, and then we get brackets. So the reason why people go wrong is they miss the fact that there are 2 different tiers of brackets. There are actually 3 sets of brackets. There are these curly brackets. There are these brackets around the y0 plus yn, which are totally useless, but since they're printed in the formula book, let's copy them. And then there are these other 2 brackets after the 2. And the reason why people do this wrong is that they miss out some of these brackets when they put them into the calculator. So a bit like the binomial, it's a good idea to start with the bracket structure. We're going to have a half times whatever h is, times big curly brackets, times an addition of 2 terms here, plus 2 times an addition of lots of terms here, and then close the big curly brackets. And all we've got to do is in the first stage, we've got to do y0 plus yn, which is the first one plus the last one, so that's 1 plus 2. And then in this bracket, okay, is all the other y's that we haven't had already. So y1 up to yn minus 1, which is these middle 3 here. So that's going to be 1.035. So you can see the table. And then plus 2 root 3 over 3 plus root 2, close bracket. And h, of course, was pi by 12. So your job now is just to do that on your calculator with all the brackets. If you miss out brackets, it will go wrong. Okay, but otherwise it's just typing it into your calculator. So here I'm starting that process, okay? I want you to see both things. Okay, so the pi by 12, you could argue, doesn't need to be in brackets. Okay, and then I open brackets twice. You could argue the 1 plus 2 doesn't need to be in brackets, but I'm having written that down. That's exactly what I need to type in. And then I do the 1.035 plus 2 root 3. Now, if these are 2 root 3 over 2, 2 root 3 over 3. Oh, no. Now, if these are horrible decimals, you can, of course, store them in your letter memories. That's the next best thing to do. That's 3 on the bottom, okay, plus root 2. And then at the end, escape from the root 2, we need to close brackets for this one here, and then we need to close brackets again. Okay, all right, and I've missed out a plus there, so you double and treble check you have typed that in correctly. Okay, and we get 1.3362. Now, what does the question ask for? So part B, part A was filling in the table, part B was working out this, and we're going to say area. It says estimate the area R. Okay, so the area equals the integral from 0 to pi by 3 of sec x dx. Notice I haven't at any stage tried to integrate sec x. I've just done this calculation, and I've got an approximation of 1.33621 from my calculator. But of course that's ridiculous. This was rounded, so that's approximately 1.34 to 3 significant figures. You do the appropriate accuracy. Okay, but if you want an answer that's correct to 3 significant figures, then all of these values, all of the values in your table, need to be correct, either exact, as most of them are, or correct to 4 significant figures, like that one there. Now, there's a double check often here that you haven't done something completely garbled, because of course we could work out a better estimate, actually, simply by typing in the integral. I can't type in sec x, but I can type in 1 over cos x. Make sure the calculator's in radians or you look very, very foolish. I can see an R there, so it is. Remember, anything involving integration, even if you're not actually doing the integration, we're approximating an integral, so it has to be in radians. And we're going to go from 0, and the upper limit was pi by 3. Does it let me do a fraction in a limit? Yes, it does. Isn't that nice? Pi by 3, that's 1/3. Okay, 1/3 pi then. So there's my integral set up, and that should give an answer something like 1.34. Okay, well, it's a bit less. It's 1.316, but that means I'm not radically out, so I don't think I've made an error. Under no account do we write down this answer, because the examiner will know you've cheated. They want you to know they want you to get a less precise answer using the trapezium rule. The calculator doesn't actually use the trapezium rule, but it uses a related method, but it uses it with massively many more strips than we've just used here. Okay, which is why it gets a better answer. And then we've got to explain whether it's an overestimate or an underestimate. Well, we've just seen it's an overestimate because that was the more precise answer. But that's cheating. We've got to explain using the diagram. Sometimes they'll say using the diagram. And we can explain in words as well. I'll say that as well. But using the diagram, first of all, to make this convincing, we need to draw the strip as wide as possible. So we're just going to draw one strip, but you need to stress that it's one strip of many. Okay, there have been stupid mark schemes where if you just drew one strip without explaining it was only one of many strips, they kind of assume that you think there was only one strip, which is balmy. Anyhow, so if we just consider one strip of many, because the graph was curving this way, the trapezium we've worked out, actually there are 3 trapeziums, but every one of those trapeziums would have had area. This shaded area is included in the trapezium, so it's included in our answer. Okay. But this is extra unwanted area. We wanted the area under the graph. We didn't want this shaded bit. So this is extra unwanted area. Therefore, we've got an overestimate. Okay? And we'll get an overestimate, and we'll get this extra unwanted area every time the curve is sort of bending upwards. Even if it's sort of, if it's sloping down, then bending upwards means doing that. That will be extra area like that. Don't necessarily copy this down. Okay. Whereas if it bends the other way like that or that, okay, we'll get the trapezium will actually miss out area that we wanted. Okay. So you either say there's extra unwanted area or there's wanted area that's been missing. But you'll see that the shapes of the graph that give you the extra unwanted area, okay, is when the graph is looking like that. Okay, and we call graphs that go like that. Okay, and graphs that go like that, well, this looks like the entrance to a cave, so this is concave, and this is convex. Okay, all right, so we get an overestimate when it's convex, and we get an underestimate when it's concave. So you can say things like, sometimes you'll get credit for a convex curve, therefore the trapezium rule overestimates. Sometimes they say you must use a diagram, in which case writing that doesn't get you anywhere. You have to draw this and you have to point to the extra unwanted area. But if you want a stupid way of remembering when you get the underestimate and when you get the overestimate, if you go back to thinking concave is the one that looks like the entrance to the cave, okay, well, caves go under the ground, don't they? Yeah? Okay, so the one that goes under, one where you get an underestimate is the concave one, and so therefore for the convex one is an overestimate. Isn't that stupid? But it might help you remember. But I'd really recommend you think about diagrams. But if you're drawing the diagram, as I say, maybe just draw one strip, but make it clear that it's one strip of many. And that's quite a long video now, so I'm going to stop. Bye.